Hello, everyone. Hope you had a good lunch. My name is Yuval Boger. I'm Chief Commercial Officer of QuEra. Maybe I will ask the panelists to introduce themselves. So, Takano-san, who are you and what do you do?
Good afternoon. So my name is Ryousei Takano from AIST. Research background is operating system and HPC, high performance computing. So now I'm in charge of ABCIQ. So that is a world first quantum computing dedicated large-scale HPC system. So I'm very busy discussing stakeholder and potential partners, including QuEra, Agnostiq, NVIDIA.
So, Elica, who are you and what do you do?
Thanks, Yuval. Hi, everyone. My name is Elica Kyoseva, and I'm Director of Quantum Algorithm Engineering at NVIDIA. My background is in quantum computing. Initially, I was a researcher working on quantum control, quantum error mitigation, and about 4 years ago, I moved to work on algorithm side, especially focusing for the last 4 years on quantum algorithms for drug discovery and for healthcare applications. I joined NVIDIA 4 months ago, and it's really nice to be part of this team contributing to developing NVIDIA Quantum and our products.
Thank you. And Oktay?
So Oktay Goktas, founder of Agnostiq, PhD from physics from Max Planck Institute, Germany. We are a startup based in Toronto, Canada. We build a software layer bridging HPC, quantum, AI, and cloud.
So Oktay, we are friends, and just between us, let me ask you a question. So AIST purchased a supercomputer, classical supercomputer with NVIDIA, and a QuEra quantum computer. What is your role?
So what we do, when you buy a supercomputer like GPU clusters, and when you bring quantum computers, so managing and doing anything on top of GPUs like AI, HPC is very complex, right? And when you bring quantum computers, it becomes even more complex, right? How do you manage infrastructure? How do you bridge that infrastructure to work together in a very efficient way? How do you manage user access? How do you make it simple? Like most of these tools from the HPC are still very expert level. You need to go deep understanding the many frameworks from Slurm to PBS to Kubernetes, right? But most of the users right now today, they just know Python. So we bring it to Python level and make it easy for the end users to compete in these platforms and to make it easy for administrators like Ryousei to manage this infrastructure in an easy way.
So when we speak about quantum and HPC, you're representing an end user. How do you see quantum and HPC work together?
Yeah, so there are 3 use cases. So first one is the simulator, so like quantum chemistry, and also the optimization, that is a kind of logistics and manufacturing field. Last one is machine learning. So we are very interested in the quantum generative AI. So we are collaborating with University of Toronto around Guzik, Professor Alan Guzik team. So we are thinking about such kind of HPC and classical hybrid computing area.
Today, a lot of people are thinking about hybrid algorithms and the part classical, part quantum. And one reason is that quantum computers are not that great still. They cannot do long calculations, so you break it up into smaller segments and alternate between classical and quantum. But Elica, do you think this is going to continue into the future? So eventually there'll be really great quantum computers. Is classical compute going to still be part of an HPC center when quantum is involved?
Yes, 100%. Our view at NVIDIA is also we have a product called Q2B24, which allows for the seamless control and job distribution between GPU, CPU, and QPU. And of course, our view is that next to any quantum computer, be it NISQ or FTQC, there will be a classical AI supercomputer. So going forward, we are also very much interested to explore what can AI do for quantum computers. On one side for algorithms, on the other side for hardware design. But classical computers will help to realize quantum.
But let me dive into that just a little bit more. So I can understand why HPC or classical HPC is really useful in simulating quantum programs during the development process. And I can understand why, as you mentioned, HPCs can help design better quantum computers. But is there something that you think could be happening during the execution of a program where a classical compute would be useful?
Yes, so for example, currently you can use classical computers, supercomputers, for error mitigation. So looking at very large circuits, and you need to do effective error mitigation on them. So we actually have a few projects looking at that, and they do require, a lot of GPUs. But going forward, when we have error correction, we would need also to have very tight integration, very fast, readout, error detection, error, not suppression, but error correction. So we would need also, when we move to the FTQC regime, we would still require a lot of classical compute to support the runtime of an error-corrected quantum computer.
You're serving a lot of users, both internal users as well as providing services to others. How do you see that users would develop code for hybrid solutions? Are they all going to be using one framework, or do you see very many different frameworks that are going to be used?
Yeah, basically, so we are open. We want to provide open platform. So we want to provide user many options, many framework, many hardware. So user can choose optimal solution among that. So that is the basic idea.
In Oktay, I think that one of the value propositions of your platform, if I remember correctly, is that you can swap fairly quickly. So maybe you're using storage on one cloud service, and now you say, okay, I want to use local storage, or I want to use some other cloud service. Do you think that will also happen in quantum, or are quantum computers are they sufficiently mature to really just make 2 lines of code and switch from IBM to Quantinuum, from Quantinuum to IonQ or other computers?
I think that's already happening. Yeah. I think that's already happening when you see, framework. So you have Penling, you have Qiskit, you have Cirque, you have Blockade, right? Many other frameworks coming into play, ecosystem. And users, they want to explore all of these tools, see, for some tasks, maybe some of these, tools are better, of course. And it's still early to really to decide which framework is going to be the the main one. And in the maturity part, that's also happening right now. So you see that players like AIST, for instance, they are buying many quantum computers because you want to explore all of these quantum hardware in parallel, because you don't know who the winner is going to be, and maybe there will be actually multiple winners in the space, similar to classical compute. And so you just need to provide that layer for the end user. It's very complex, and you need to provide that layer that it's very easy to swap from one quantum computer to the next one, but still keep the flexibility that they can go as deep as they want, right, in terms of the customization.
So I have a question for all 3 panelists. Classical HPCs has been going on for many years. Now there are all these new kids on the block with their quantum machines and qubits and so on. What should quantum vendors learn from HPC vendors when it comes to management or service or installation? What would you like to teach the quantum vendors in this audience?
Yeah, so the quantum and HPC are quite different in many aspects. For example, technology and user community. So HPC area, so we are established user management and billing system. But also how to, open question is how to integrate quantum computing management into such system, or otherwise, so creating new one. So, anyway, so we need to share best practice or experience in HPC and quantum hybrid system operation. So, so that sharing information and exchanging opinion is very important.
In Elica, I think NVIDIA GPUs power 1 or 2 HPC centers in the world. What do you think that quantum vendors should learn from classical HPC vendors?
Something that NVIDIA did really good on the classical side is basically with the CUDA framework, it enabled domain experts to start using GPUs. And I think this is also what is very much required and expected from us as a quantum computing community, to enable really the domain experts to start using the quantum computers as they mature without having to go to, kind of middlemen or consulting services or etc. So I think this is something we can really learn from classical HPC, and in particular also how NVIDIA enabled it.
In Oktay, do they need to learn anything or just connect to your framework and you take care of the rest?
Yeah, I think I want to go maybe on the opposite direction. What is different between the quantum and HPC? So when you look at the HPC traditionally, it's all experts, mostly academics having PhDs from different fields like chemistry, physics, right? Like very, very deep expertise in the HPC space, and it's still like this, right? But when you look at the quantum space, actually, interestingly, it's not surprising to see a lot of high school kids already doing quantum calculations, right? From the very beginning, it's very accessible, actually. Like you can see, many of these quantum frameworks being available, and some of the high school kids, undergrads, already exploring these tools and becoming expert how to use these tools. So it's a little bit different, but of course, like quantum space needs to learn a lot of things from HPC, how to develop really robust tools and software layer stack for quantum computers, and quantum computing is part of HPC anyway, right? Like it's another way of doing HPC, right? And it's very, very integrated.
I think if you did a survey of this, let's go back in time to the first Q2B Tokyo 2 years ago, and if you did a survey of this audience, they would say, oh, quantum should be on the cloud. No one would want on-premise quantum computers. Now, of course, I'm very thankful that you decided to buy a quantum computer, help me make my quota for the year. But why on-premise?
Yeah, so how to say, so user require very low latency communication between HPC and QPU system. So, for example, VQE or such kind of iterative algorithm require a low latency. So we want to install, set up on-premise quantum computer, and also this is we want to set up. So ABCQ is a kind of a hub among the on-premise quantum computer, and we want to so open, democratize quantum computer using this platform. So on-premise computer is very important for us.
In Elica, I think that as fast as NVIDIA GPUs are being made, there's never seemed to be enough. Do you also think that customers buy on-premise quantum computers because they're worried that they're not going to have enough capacity on the cloud, or are there other reasons why you're seeing on-premise quantum computers?
I think on-premise quantum computers are great, especially if they're integrated with, AI supercomputer. And except for, in addition to building a community, building algorithms that require low latency, something that is very important is also creating digital twins of QPUs. And this really helps the vendors make better hardware. So I think this is also one of the reasons that we always want to work very closely with the different hardware providers, including you, QuEra, because we think that classical AI supercomputing can help with the build-up of hardware, quantum one.
And Oktay, any thoughts from you on why people would want on-premises?
Yeah, I think one of the critical things is data locality, right? So there is a lot of players in the space, like including government, defense, and academics. You don't want to expose all of your data to the cloud, and you just want to have control over the user management, access, and data locality. So that's a big, critical component that keeps, I think, quite a lot of quantum computers on premise, accessible to the set user of, limited user base, just because of the security and I think privacy.
One of the things that we see, if it's okay that I add our perspective to this, is that a lot of countries and a lot of regions are building national and regional quantum computing programs. And what they're looking for is not just hardware, but also to build a community, as you mentioned, and also sometimes build a startup or a small company ecosystem accelerator to go with it. And fortunately or unfortunately, they want the computer locally. So the Finland, just as an example, the Finland national program does not want a computer in Boston, Massachusetts. They want a computer in Finland. So that's one of the reasons that we see. And it turns out, I remember speaking with the CTO of IBM Quantum, and he said, well, once we deliver the quantum computer, usage has gone substantially higher, even though the customer could have used the same computer on the cloud. The fact that it was in our lobby was a big thing. When you think about physical installation of quantum computers, is there anything different that you're seeing, or is it just like another AI compute cluster?
So physically, so I'm not expert with hardware, but quantum operation and the HPC operation is quite different. So the quantum computer working, how to say, so the need calibration, and there are a lot of unique substance and so on. So we don't want to black box of quantum computers, so we need to open such kind of operation, and how to say, yeah. Please go ahead.
So you see these differences.
Yeah.
Elica, how would you think about? I know you've only been a few months in NVIDIA, but NVIDIA has gone through the transition from CPU only to CPU and GPU. Is the QPU that different, or do you think just there's going to be CUDA for everything?
Yes, and even now CUDA-Q supports all of these, so you can have QPU, CPU, and GPU backend. So yeah, we definitely think that NVIDIA's products, in particular CUDA-Q, which is our framework for hybrid quantum classical simulations, will support all of these different architectures.
Oktay, I wanted to ask you, and then maybe the other panelists, what's new? What have you learned in 2024 that you didn't know last year, as it relates professionally to quantum?
For quantum, I think I've seen a lot of quantum computers being like either getting ready to deploy in on-prem, or or already being deployed. And what was new for this year, like people were expecting some like kind of winter for quantum, right? And I think like this year was just proving it false, right? That the quantum computing space is growing fast, making good progress, and interest is even getting bigger, right? I think that was in the quantum space new for me.
And Elica, both from your NVIDIA experience and earlier in the year, you were still with Wellcome, I think. What have you learned this year?
So I learned a lot. But I would like to point out something on the algorithm side. It's actually coming from NVIDIA and Alan Spuru-Guzik and partners also at St. Jude. But it was the first transformer AI model for finding the ground state of molecules. It's called the Generative Quantum Eigensolver, which, even though it sounds like VQE, it is actually a very different type of model. And what it enables is basically the classical AI model to generate the circuit without any variational optimization, which reduces considerably the requirements on the quantum side. I think this is really the first model and the first algorithm that effectively uses AI for quantum circuit synthesis. It can be really expanded to many different types of applications. So this is something that I learned, and it's very exciting. I think this is a new field that is opening in quantum algorithms.
And Takano-san, what have you learned?
Yeah, so I'm a newcomer in the quantum computing area, so everything new. But transition of FTQC is quite fast in moving, so that is very impressive. For example, so last year, end of last year, QuEra published a paper in Nature, so that is very impressive.
Very good. One of the things that quantum computer vendors talk about is power consumption, whereas a classical supercomputer takes megawatts of power. I mean, I know that the existing QuEra computer takes 7 kilowatts of power, and the next generation, maybe it'll be 10 kilowatts. How important is it, or is it important at all, that quantum computers take less energy?
Yeah, it is a very important point for as well as quantum computers.
And is it just because of sustainability goals, or is it related to infrastructure in the data center? Why is it important to you?
So money. So yeah. In Japan, so our energy cost is very high compared to other countries. So the power consumption is very important issue.
Interesting. So Elica, when people want to buy, setting up a new center, and they want a supercomputer, a classical supercomputer, and a quantum computer, do they talk with NVIDIA, or is it two separate conversations? One, they just pick a quantum vendor, and then they go to NVIDIA or someone else for the classical supercomputer?
In principle, they would talk to us, and then we basically enable everyone. But usually, of course, these are complex discussions that take several steps, and we are part of all of them.
And Oktay, I wanted to ask you about the balance between quantum and AI. Do you see a big shift where people are just, oh, this quantum stuff will never happen, or will happen in 5 years, I'll have another job by then or something, and just focusing on near-term AI? Or do you see them progressing side by side?
I think past year, there was excitement, big excitement, right? A kind of exaggerated excitement about AI. It's coming to a reasonable level, and now quantum and AI going side by side. Eventually, you have quantum in every, the way that GPUs are part of every compute stack, quantum is going to be part of, every compute stack as well. Of course, that might, take years, doesn't matter. Eventually, it's going to be there. But right now, I think quantum and AI is making progress side by side. Of course, quantum is not as big as AI. Right now, AI is dominating all the space, I guess. And it's going to take, go that way quite a while, probably, since we get, first useful quantum computers being part of production workflows. That's going to that way. But I want to comment on the maybe going back to the energy consumption question, which is not very much emphasized in the quantum space. When you look at the past 10 years, the way that machine learning AI workloads consume compute, it's exponentially scaling, right? So in 2012, the first deep learning algorithm was running in a laptop, maybe a desktop computer. That was the best machine learning algorithm in the space, right? Now the best machine learning or AI algorithm in the space, like think about ChatGPT, like GPT-4, or for equivalent of these other ones, Llama and one, like these consume like exponentially larger compute, and takes months and sometimes years to train these systems, and the energy consumption is very big implication for the planet, for the humanity, for the climate, right? And when people think about quantum computers, mostly like you think about complexity classes and what is the scaling. But even you put classical computers and quantum computers side by side, and they are solving the same problem at the same time. And the power consumption is very low, and which is a big business value, of course, right? And I think that's something that is kind of undervalued. I think we need to emphasize that again.
So I have several more questions, but please do submit your own using Slido, and if we have questions, then we'll take them in a couple of minutes. I did want to ask about AIST. I know that there's ABC-IQ, which is a classical supercomputer that's, I believe, built by Fujitsu. And I saw an announcement that you're doing ABC-I3, which I think is an HPE machine. Why do you need two?
So the quantum computer and the hybrid computer, both of the two are very important for Japan. So the generative AI is a kind of extend our industry competitiveness. So the generative AI mass infrastructure is very important, and also emerging technology like quantum computing is also important for next AI generation, AI era. So we invest, our government invest both of them.
Understood. By the way, are there any questions from the audience?
There's one. We have a question, a person asking, what could be challenges when trying to implement HPC quantum applications?
What could be challenges when trying to implement HPC quantum applications? So, Elica, go ahead, please.
Identifying the correct use case and being able to reduce the problem size so that you can do the most effective, larger part of the problem on classical AI supercomputer, and just doing the small size, very difficult, ideally exponentially hard problem on the quantum computer. And, it is a general recipe, but it's actually not very easy to identify these problems and to be able to solve them in such a way. So it's a very active area of research.
So, and I certainly want to hear your answer, Oktay, in a second, but Elica, what would you recommend as the process? So, customer has a problem, they're considering quantum. What would you recommend that they do to find that right algorithm?
I was, before that, in the end user. I was working in industry in a pharma company that was end user of quantum computers. So we were developing algorithms for drug discovery. And it's really very important to remember that industry is not staying behind. They're developing really the best models classically as well at the moment. And when we want to show them the benefit of quantum computing, we really have to target provable advantage, of algorithms for a particular problem. So I think it's very important that we don't offer them solutions that involve quantum computers when there are perfectly good classical solutions out there. This is the first step, really identify the problem, and only after that try to develop the quantum solution to that.
And Oktay, what would you say the challenges are in building a HPC quantum classical application?
Yeah, I think many right now, like quantum computing is complex, HPC is even more complex, like, you know, like you are dealing with 1,000 cores of CPUs, 1,000 cores of GPUs, and now one or two, and maybe in the future, like many quantum computers all together, and managing like data, you know, for especially for hybrid algorithms, managing, you know, all of this data, allocation between quantum and classical part, and which part of the compute goes to quantum, which part goes to classical, how to schedule all of these things efficiently, timely. Like there's so many critical parameters that you need to think about, of course. Maybe some of these parameters are not going to be that critical when you just, you know, experiment, run a POC. But when these POCs one day turn into a production workload, these things are very critical. Like the implication is big because all of these things are very costly, right? GPUs are very expensive, very scarce. QPUs are very expensive, very scarce. So everything needs to be extremely optimized for running these jobs.
So if I were to summarize what you both said, then Elica spoke about the what is you trying to do, and you spoke about the how to actually do it. So together, that's how you build a
Yes.
quantum application. Do you have additional insights on what are the challenges in building such an application?
Another aspect, so that from operational operators aspect, so the co-scheduling of quantum resources and the quantum classical and quantum resources. So the quantum and the classical is very different. For example, so the quantum resources are precious and the runtime is quite short. And on the other hand, HPC resources are much more abundant, and also runtime is quite long. So it is difficult to efficiently utilize both of the resources. So that is the open issue to the operation side.
When I speak with customers, sometimes I ask them, where are you today in your quantum journey? Where would you like to be in, say, 2 years' time? And what's stopping you? Well, why are you not there already? What has been your experience, Elica? What's stopping customers today from being where they want to be on quantum?
The main thing I would say is not understanding so much the technology and not seeing it as advanced, let's say, as classical computing. So there is still a lot of companies that are considering quantum solutions to some of their computational problems, but ultimately, you know, still stay behind and don't invest. So they, I think, want to see really first use cases of applications, really changing businesses or making money for a business, making a difference before they jump into their quantum journey. So there are some that are still kind of playing safe and not diving in.
And Oktay, what do you think is stopping customers, or what the barrier to them being where they want to be?
Yeah, I think like patience. So if you go back to 2015, let's say, and you are just like walking in one of these big city streets, like you know, take any tech hub, either San Francisco, Tokyo, Toronto, doesn't matter, right? And you just hear the word Gen AI, generative AI, right? And like, who cares about generative AI? It's going to take years, and you know, people that invested in generative AI, now they are at the front line and taking advantage of that technology, right? And same for quantum. For every new technology, it takes time. You just need to patiently work in that space to be, you know, resilient and invest in the space, learn about it, and one day it's like just returning back, right? And quantum, I think that's something happening in the quantum space. I see that people getting companies, clients, people getting tired of maybe it's taking long, but that's for every technology. Like look at AI, it started 50s, and the big like social impact, of course it was there, but the big social realization came, I think 70 years later, right? So it takes time.
So you're saying that AI was, say, 50 years in development and then was an overnight sensation, except no one knew that. So what is your guess on when quantum will be an overnight sensation? When will it be, and maybe what do you think the application would be?
Yeah, so that's an interesting question because like AI was part of our everyday life, but that sensational time didn't happen before ChatGPT, right? So for quantum, what's the application that is going to make that? I don't know. But I once had a discussion with one of physicists like big in the field, and later on he got a Nobel Prize. I don't have permission to mention the name, but he was saying that one day we will have quantum computers in every pocket. And I think that's going to happen one day, but that one day might be 100 years away. I don't know, maybe 20 years, maybe 5 years, maybe 10 years, right? But it's going to happen. So every electronic device is going to have some quantum parts. When you go to a hospital, that already happened, right? Like you see a lot of quantum technology there in usage, and why not for computers? Same thing is going to happen for quantum computers as well.
I don't think I have your patience to wait 20 years. And by the way, I don't think I need a quantum computer in my pocket. But when do you think that moment will happen?
It's tough questions, but I'm an optimist, so it must happen. I'm not sure sooner or later, but yeah, I hope maybe. Within 5 years, I'm not sure.
Of course, it's a tough question. If it was easy, we'd have marketing answer it. What do you think, Elica?
My answer would be also 3 to 5 years. And I also disagree with Oktay. I don't think we'll be carrying quantum computers in our pockets, like probably ever. But I think it will be part of many of the services that people use and are not even, aware. For example, of course, in banking, in security, maybe in drug discovery, materials simulations. So I think that it will be more like the businesses that will be using quantum computers, not so much the end user. But I'm also a big believer, and I'm very enthusiastic about algorithms for early fault tolerance, because most of the applications that we currently know, especially around material simulation, drug discovery, chemistry, they require very deep fault-tolerant quantum computers for months of runtime, maybe years. And like having early fault tolerance is where I think we'll see the real value, which will be, I really hope so, like 3 to 5 years from now.
And I don't think we have classical supercomputers in our pocket, although maybe the iPhones or whatever phones we have in our pocket would have been considered supercomputers many years ago. How are we doing with audience questions?
There's actually a lot coming in. I would say maybe I'll try to bundle some of these questions, but I think there's a lot of questions about how do you find the useful, sorry, I'll just go back to the actual question, which is how do industry leaders find useful problems to solve? Then there's the question of how do you find the right partners? And then how do you determine the right balance between HPC and quantum? So that was one question. We also have a bit more specific questions around, from an HPC perspective, are there any requests for quantum computer system architectures other than just qubits, quantum RAMs, storage class memory network, etc.? So I'm just bundling for you.
So let me try to answer the first question. And I think Elica touched on this earlier. Not every problem is a good candidate for a quantum solution. And not every problem that is a good candidate for a quantum solution is a realistic quantum solution today. So what we do at QuEra when customers come with problems, we sometimes have these joint sessions where a customer presents 3 or 4 problems that they care about. We present 3 or 4 solutions that we've did that seem to be in the similar field. And then hopefully there's an overlap and we say, hey, let's identify a problem that we think could be a good fit for our computers and that may be useful to you. So in 10 seconds each, my favorite question, dinner with one of the quantum greats, dead or alive, who would you go with, Elica?
I heard the question in the morning, so I was thinking the same what you answered, so I'll still stick to that, and I would go with Einstein. I mean, he was a real genius, so I would go with Einstein.
And Oktay, 5 seconds.
Since she took Einstein, I'm going with Newton.
Feynman. Feynman.
Very good. Well, I think we're out of time. Thank you for my panelists, and thank you for this wonderful audience.